going to start with a real basic introduction of statistics to make sure we're all on the same page. So statistics really applies to two separate types of problems. The first problem really associates with taking the data, summarizing it, describing it, and exploring it. The second problem deals with using the sample to infer the nature of the data from which the sample was selected. So that gives us more of our inferential statistics. All right, descriptive statistics is that first issue that we were talking about, right? It's really associated with the organization, the summation. If I could spell summation, right? And description of the data. So a good example of this, we have an environmental engineer who uses statistics to describe the data set, and that data set consists of daily emission of sulfur oxides from an industrial plant recorded for 365 days last year. So they're just trying to describe what that data is and what it means. Now on the other side, inferential statistics, definition is pretty easy. They're trying to make an inference about a large set of data. So inferential statistics is trying to make an inference. So sometimes when we look at that phenomenon of interest, we're going to characterize it by a data set, and sometimes that data set can be physically unobtainable, or it's too costly or too time-consuming to obtain. So let's look at an idea of we want to look at the drinking water quality on an inhabited but remote Pacific island. You might expect the water quality to depend on, maybe temperature of the water, the level of the most recent rainfall, etc. So if you want to measure the waterfall or the water quality repeatedly within the same hour at the same location, quality measurements are going to vary, even for the same water temperature. So if you think about, how much is it going to cost you to be able to get a sample of that water quality on that remote inhabited island? It's going to cost you a lot of money. And if it's a remote island and we want water quality from every stream, you just simply might not have enough money to do so. So in those cases, the population is our entire water quality sample that we want to collect. And we can go ahead and take a greater look at that and say, well, we can't collect the entire population, but we certainly can collect a smaller subset of that data, and that data is then called our sample. So most of the time, we're actually looking at a sample and not at the population. And we're going to try to take that data sample and describe our population through inferential statistics. A few other definitions. We already talked about the population of the sample, but the population is really the data that we want to describe. The sample is just a subset of the data from the population. And the experimental unit is the object upon which measurements are collected. and then the variable, those are the actual characteristics. We can also call it properties. Of that experimental unit that's in the population. All right, so let's look at an example. We have engineers in Kentucky. They've collected data on crashes that occur at intersections in Lexington. One of the goals was to estimate the rate at which the left turn crashes occurred at intersections without left turn lanes, and then use that estimate to develop numerical warrants for the installation of left turn lanes at all intersections. So the engineers collected data at 50 intersections without left turn lanes over 1 year. And at each intersection they monitored the traffic, recorded the total number of cars turning left that were involved in the crash. So let's go over a couple of quick example questions. What's the variable in the experimental unit for the study? Well, the experimental unit for the study is we're looking at intersections that do not have a left turn lane. And then the variable that we're collecting on the intersections without the left turn lane so the total number of cars turning left that crash. What's our target population versus the sample? Well, the sample, we know we collected data at 50 intersections. And it's in the Lexington area. And then the population are all the intersections. And what inference do we want to make? They're going to use the sample data to estimate. They're going to estimate the rate at which left turn crashes actually occur for all of those intersections. Now, reliability is also a part of inferential statistics. Generally, it accompanies an inference, so an inference really is incomplete without the measure of that reliability. If you think about science between fortune telling and science, a palm reader, they're going to sample your hand and make an inference about the population, which would be your future life. However, their palm reader's inferences really don't have a measure as to how likely the inference is to be true. So we really want to look at what is that reliability that we have associated with that inference. So let's go back to this example to kind of answer this question. What are the really engineers interested in? Are they interested in a very specific crash rate? Probably not, right? They just don't want one crash rate. Because we know when we talk about real life, let's just not talk about weather people, Every time we do something, there is an error of estimate. So error of estimation, that's the difference between the sample crash rate and the population crash rate. So that's just the difference between our sample and our population. Now, when we have statistics and inferential statistics, we can actually bind that, right? And the way that we bind our error of estimation is through some type of confidence interval. So we can bind that number by 10%, by 5%. If we say it's 5%, then we are 95% sure of our value. And if we do 10%, we're 90% sure of our value. So that's really the difference between science and essentially fortune telling. Now you can ask yourself the question, where do weather folks fall in there? And I'm just going to let you answer that. So types of data, generally two types of data, quantitative and qualitative. Quantitative, anything that's essentially associated with a numerical scale. It is measurable, right? Measurable on some type of numerical scale, such as the breaking strength of steel pipe, and that would be in pounds per square inch. Qualitative is more of a classification. Doesn't really possess any quantitative interpretation. Like the type of a crash. It could be a left turn crash, a right angle crash. We can quantitatively describe each of those crashes, but they're different categories. They fall into different categories. Now we can also say qualitative is that Likert scale, or Likert scale. You can categorize yourself 5, 4, 3, 2, 1. 5 is I strongly agree, 1 is I strongly disagree. That is really quantitative or qualitative data that we're trying to put in a quantitative way. All right, let's look at an example. So we've got a journal reporting performance dimensions on water distribution networks in Philadelphia area. We have variables measured. The pipe diameter, obviously that's quantitative. The pipe material, steel or PVC. Now that's a qualitative because it has to fall into one or two categories. A pipe location, that would be qualitative. And a pipe length measured in feet, that would be quantitative. So why do we care about statistics? Well, because the sample is not going to provide us an exact image of the population, and the nature of the information provided by the sample actually depends upon the sample that was chosen, and the inference associated with that sample would vary if you changed the sample. So let's think about this for a second. You want to estimate the proportion of all steel alloy failures at a petro plant that are caused by stress corrosion cracking. We're going to look at a sample of 100, and we find that 47 of those were caused by stress corrosion cracking. So does that mean that actually 47% of those alloy failures are caused by stress corrosion cracking? All right, what happens if another engineer finds a sample and there's only 42? So who's correct? Is it the person that found 42 or the person that found 47? Maybe the true percentage is 44 with a 5% confidence interval. Right? So any inference you make on the sample is always subject to some level of uncertainty. So if we said our true percentage is 44%, and we're absolutely sure by that about 95%, all right, so if you take 5% of that value, we're going to bound it by 5%, so 44 minus 5 would be 39, and 44 plus 5 would be 49. So we would expect At a 95% level of confidence, our percent values to fall between 39 and 49. So then when you look at either of these first two engineers, they are actually both correct because they both fall within this 95% level of confidence. All right, now you've got a third engineer that found a failure rate of 81%. Okay, well, now we can say that 81% is an outlier, right, because it's unusual. It falls outside of our 95% reliability and inference, so this 81% must be an outlier. Now, when we think of outliers, there must be reasons why it is an outlier. What sample did this engineer look at? Did he happen to look at the pipes that looked older? Well, if he's looking at older pipes, maybe, of course, they have stress fractures. So again, it all depends upon the sample. All right, so let's answer the last of the questions of why do we actually care about statistics? Well, it's going to enable us to make decisions based upon inferences about a population with a known level of certainty or reliability. So because of that, we can make some intelligent decisions, and it also allows us to think critically about our data, which is very important because we need to explain our data to those that are not engineers, and having these nice inferences and our reliability associated with that gives the population some level of confidence within, for us, in what we're doing.